Okay, so this presentation is about a new project. The name of the project is Stage 1 Xen, and the goal will be apparent soon. To understand what Stage 1 Xen is for, I'll start by talking about Rocket. Rocket is a container engine, just like Docker. It's a Docker alternative, in fact. It was started by the CoreOS guys about a couple of years ago as a security-focused Docker alternative. For example, one thing that the CoreOS people didn't like about Docker is that Docker runs, in order to run, needs a daemon, long-lived daemons, always running, which runs as root. And it's considered not a good practice from a security point of view. So the first thing that they changed in Rocket is that Rocket doesn't have any daemons. It's just one command. You run the command, you execute it, and then when it terminates, it terminates. The command line utility is called rkt, but the project name is Rocket. You use it pretty much like Docker, so you can fetch images from the Docker registry, you can run them, you can list the running containers, you can mount volumes into a containers, and so on. Yeah, very, very similar set of operations. Is a clean implementation of the Open Container Initiative standards, so like the image format specification and the runtime specification. As I said, it supports pulling containers from the Docker registry, just like Docker. However, Rocket tries to do more signature and integrity check verifications to the images compared to Docker. Again, from a security perspective, it pays more attention to details. And this is all good. I mean, it's featureful, it's Docker, but a bit more secure, so it's all nice. But to be honest with you, this is not the reason why I picked Rocket. Rocket is actually very, very well engineered, very well architected, and that is actually the reason why I chose Rocket. So the rocket is based on the idea of stages, just like a real rocket. So there are 3 stages, stage 0, stage 1, and stage 2. Stage 0 is the one that takes care of pulling images, unpacking images, placing them on your file system at the right place on your host. Stage 1 is the one in charge of creating a new execution environment for your container to run, and stage 2 is the actual container application running. And these 3 stages are completely separate. Before I get into more details about these stages, I'm going to spend a couple of minutes to rant about the word containers, because that is actually overloaded and very confusing, mean different things to different people. So at the very least, containers means 2 different things in particular. So on one end, container is a packaging format. Is whatever you download from the Docker registry. So it's in the same realm as RPM, deb, right? It's an application, it's a binary packaging format. That's what it is, right? So you can download an image from the Docker registry, and then, honestly, you could do whatever you want with it. You could unpack it, you could run it, not run it using Linux namespaces, you could run it using virtualization, you could run it on Linux, you could run it on Solaris, you could do whatever you like. Because in fact, it's a packaging format. On the other end, many people use container also to mean the technology based on the Linux kernel to actually create a running environment for this application. But this container doesn't really have a meaning in the Linux kernel, really. The real name of this technology is usually Linux namespaces and C group. There isn't really a single name to cover them all. But the matter of fact is, Linux namespaces were not invented to run application packaged in the Docker packaging format or in the OCI Open Container Initiative image format specification. So you can run Linux namespaces to run any sort of things, including to restrict some of the operation of your own normal application downloaded from with apt-get, for example, right? So these are completely distinct technologies that have nothing to do with one another, right? So on one end, you have a packaging format. On the other end, you have some namespaces on the Linux kernel. And it happens that many people call them with the same name. Now, for clarity, in the rest of this talk, I'm going to try to use cloud native app as a word to mean the container as downloaded from the Docker registry. And I'm going to use Linux namespaces to talk about the technology based in the Linux kernel that are often employed to run these applications. Right, so let's go back to the stages. We have 3 stages of execution. So stage 1 is the one, well, it's implemented in the Rocket binary, and is the one that mostly deal with cloud-native apps. So you download the cloud-native apps, unpacks cloud-native apps, deal with the format, deal with the manifest, and place it in the right file system path. And then you have stage 1. Now, stage 1, as I said, is in charge of creating an execution environment for your cloud-native app. But the matter of fact is, stage 1 is completely separate from stage 0. So much so that stage 0 is implemented in the Rocket rkt binary. Stage 1 comes from a separate repository, is built separately, is distributed separately, and lives in a separate place, is a tarball, is completely independent. It's not just a different box on a whiteboard, right? When you do an architectural design, you draw a line, in practice the code is all entangled. No. So here is actually 2 different things entirely. So basically what Rocket does is unpacks the stage 1, which itself is basically just a tarball, and calls a known application called basically run within this tarball. And this run application is in charge of creating the execution environment. And it can do in any way it likes. So it could use Linux namespaces, it could use only some Linux namespaces, it could use all Linux namespaces, it could use Xen, it could use KVM, it could use Solaris, it could take the image and upload it to AWS. It's completely free or implement in any way it likes. It could be even just, execute the binary and whatever without any isolation whatsoever. And then stage 2, you finally get to the application running in this environment. Now, in this picture, there is another interesting detail you might have noticed. You might have noticed there are 2 stages run by one stage 1. Why is that? Well, I don't know many of you are familiar with Kubernetes. Kubernetes is actually what most people use to run containers. It's a container orchestration engine. So it deploys different applications on different hosts, even with very, very large deployment, with hundreds of thousands of cloud-native apps. So Kubernetes doesn't actually schedule containers. Kubernetes doesn't actually schedule cloud-native apps. What Kubernetes schedules is a pod. So the minimal scheduling unit of Kubernetes is called pod. And a pod is just a small collection of cloud-native apps, usually 2. Typically, you have a server like NGINX and a log parser. So the application that parses the NGINX logs and maybe flags if something wrong is happening. This is a classic pod. Now, these two cloud-native apps, so the server and the log parser, obviously they need to share some of these namespaces. Like, for example, the log parser need to access the files, the logs of the NGINX. So they usually share namespaces. And this is why the minimal running unit of Rocket is actually a pod. Rocket asks stage 1 to create an execution environment for a pod, and then stage 1 create one execution environment and run the 2 apps, the 2 cloud-native apps for the pod inside this environment. But for all intents and purposes, for the rest of this talk, let's just assume that one pod equals one container or one cloud-native app, basically. So obviously the default with Rocket is the same as the default with Docker, and is using Linux namespaces, the default stage 1, okay? So before I get into why you will want a different stage 1, I'm gonna mention a few words on why Linux namespaces, are not ideal, are not perfect. The problem with Linux namespaces is that you have a shared kernel image and all your cloud-native apps running on this single kernel image. And the interface between cloud-native apps and your kernel is quite large. The syscall interface, right? Being so large is actually difficult to secure. There's a few privilege escalation vulnerability newly discovered every Linux release. So eventually, if you install a malicious app or an app that has been compromised for any reason, not on purpose, right? This malicious app, over time, will be able to exploit one of these privilege escalation vulnerabilities, break into the kernel, and from there, basically take over the host, including the data of the other apps, right? It's a security problem. So this is a very, very well-known problem in the industry, right? So if you went to any of the container conferences, there are always a lot of presentations, discussions on this topic. There have been many white papers being written on this topic, right? So it's a known issue, and everybody's trying to address it, right? I picked one white paper, which I think is interesting, but there are many. It's quite well written by the NCC group. It's called Understanding and Hardening Linux Containers. It's quite long, hundreds of pages, so I'm not going to try to summarize it here. I'm just going to give you some small points, some bites from it. Note that even these guys that I'm telling you, they are very knowledgeable. I mean, the white paper is very well written. How did they title it? Understanding and Hardening Linux Containers. So what is it are you hardening? Are you hardening the packaging format? Or are you hardening the running environment? Well, they're not hardening the packaging format. So if there is a bug in the packaging format, you're stuck in with it. So they're trying to harden Linux namespaces. Right, so what are these suggestions? The suggestions are to use SE Linux, to drop privileges, to drop capabilities, to use C groups, to apply GR security patches, to build your own custom kernel, to use seccomp, to do logging, and to use virtualization if possible. So, without going through the whole list, what is the takeaway from these lessons, right? The takeaway is that securing Linux namespaces is actually possible, but it's very, very difficult. And it involves the use of technologies such as SE Linux and seccomp that not only are actually very difficult to use, as a matter of fact, if you search how to disable on Google, the first suggestion for completion is actually how to disable SE Linux, right? Not only these technologies are difficult, but also to configure them correctly, you also often need, especially in the case of seccomp, detailed information of the application running inside. So you might have to build different seccomp profile for each of your application and for each version of your own application. So can you imagine doing this at scale with hundreds of thousands of cloud-native apps running simultaneously on your data center? So it's actually a daunting task to do at scale. Right, and at the end of the day, virtualization is still recommended. So at this point you might ask, all right, so containers are pretty cloud-native apps are pretty popular, so what people actually do, right? There must be a way to run them. Well, what they do is they use virtualization in a way to create the isolated environment, and then they run multiple cloud-native apps on top of the VMs. This is the most classic configuration. So basically, because Linux namespaces themselves don't support multi-tenancy, are too unsecure, what you do is you allocate different virtual machines to different users, so that each user is free to install any cloud-native apps he wants on top of these virtual machines. This way, if a user deploys a malicious apps, one or more malicious apps. The only ones that are at risks are his own other apps inside the same VM. Is not compromising cloud-native apps of other users, for example. Obviously, this kind of works, but has also very strong limitations. So one limitation is, first of all, now you have to keep track of two levels of resource allocation. So you have to keep track of allocating VMs to different groups or different users, and then allocating cloud-native apps on top of these VMs to these users. And also, if a user by mistake, by error, installs one malicious app, still all the other cloud-native apps are at risk within the same VM. So can we do better than that? So I think we can do better than that, right? And this is where we go back to the beginning, Stage 1 Xen. Stage 1 Xen, which is a project under the CoreOS umbrella, so it's available on GitHub under the rkt project. It's called, well, unimaginately, it's called Stage 1 Xen. What it gives you is a running environment based on Xen virtual machines. So Rocket works exactly the same way as before. There is no changes to the command line. The user doesn't even know that there is Xen underneath. The user is completely unaware. But what matters is when it's running a containers, instead of using Linux namespaces, Xen VMs are started. So now you have a much more secure environment, secure by default, without having to mess with SC Linux or seccomp. So the process of using Rocket and Kubernetes doesn't change at all. So you have a seamless user experience. However, now, again, as I said, it's secure by default. It works seamlessly on the cloud or on bare metal, and you can mix and match cloud-native apps with legacy applications. So now you can have Windows running, Windows XP on a VM running alongside your cloud-native apps, and you still have only one level of resource allocation to take care of, only VMs. You don't have to, to take care of these two levels of resource allocations, VMs and cloud-native apps, and keep track of the dependencies between cloud-native apps and VMs. Okay. Right, Stage 1 Xen, as I said, is based on Xen. So why Xen? Mostly for a couple of reasons. The first reason is the security process. So the security process of Xen has been called the best in the industry. It's very transparent. It's very easy to keep track of the XSAs that are outstanding, to apply XSAs, to figure out if an XSA affects your configuration. It's not the same with other open source projects. You probably try to keep track of CVs. It's a mess, right? So you don't know exactly which CV applies to which configuration. Usually Red Hat issues its own CVs for RHEL. Ubuntu issues the CVs for for Ubuntu products. And what if you're using, let's say, Rocket from source? You basically are on your own. So with Xen, actually, you don't have that. Stable trees are maintained for security for up to 3 years. And in general, we have far fewer privilege escalation vulnerabilities than Linux namespaces. The other reason is cloud support. Now, as x86 maintainers, you're going to hate this, so beware. So most other hypervisors, including KVM, require VMX to run. And to be honest, this is 2017. As far as I know, you cannot actually buy a machine without VMX, right? It's impossible, even if you want to. However, there is one class of hardware which today comes without VMX, which is cloud instances. When you get an instance on AWS or on Google Cloud Engine, it's still without VMX. Yes, technically, we all know that Xen or KVM can be configured to export nested VMX, but nobody does. So as a matter of fact, today, one of probably maybe the largest possible pool of machine that people use actually does not support VMX. And this is where Xen has actually a very strong advantage, because Xen can run in this environment, while other hypervisors cannot. So Xen can run on top of Amazon AWS, can run on top of Google Cloud Engine with PV guests, and at the same time can also run on bare metal and take advantage of VMX when available with PVH. And PVH is a great match for this project. Right. So what is the base architecture of Stage 1 Xen? Stage 1 Xen is, first of all, let me tell you, it's quite early days. But basically, it's written in Bash and Golang. It calls into the Excel binary to create VMs, stop VMs, connect to the console. It's using 9PFS, the new Xen 9PFS protocol to share the cloud native app file system with the VM. It distributes in ACI format. This is exactly the same format as cloud native apps. So it's basically a tarball with the binaries, all the dependencies, and the JSON file as a manifest. And it supports multiple networking modes. Just a second. I can do it. Right. It supports multiple networking modes. So Rocket comes with a multiple networking settings, like bridging, NATing, and host mode. Like you can, for example, have your cloud native apps bind ports on the host network interfaces. Stage 1 Xen maps these the Rocket networking modes into Xen networking modes. So if the user requests bridging, Stage 1 Xen uses VIF bridge, the classic networking, net front, net back bridging mode. If the user requests NATing, then Stage 1 Xen uses VIF net front, net back with a VIF NAT script. If the user requests host mode, then Stage 1 Xen uses PV calls. Let me spend a couple of words on PV calls. So PV calls is a new PV protocol to forward POSIX function calls from guest to host. After all cloud native apps are POSIX applications, so working at the POSIX level is actually a pretty good match. And what you can do with PV calls, for example, is to forward all networking calls from your guest to your host. As a consequence, now you work at a much higher level interface. It's actually much easier to virtualize. But one interesting point about this is that monitoring the VM becomes much more easy. So one of the recommendations on container was actually doing monitoring, if you remember from the white paper. And Xen actually supports extremely powerful ways to do monitoring, right? For example, mem access, the VM event interface, right? Memory introspection. However, memory introspection is also very expensive, right? It's all a new world, right, to use memory introspection. With PV calls, you get performance that today is better than net front, net back, but you also get a lot of information on the network accessing pattern of your VM. You get it in DOM0 for free. So it's actually quite easy to build an agent that takes this information and figures out if your guest is misbehaving. For example, if your NGINS containers open port 22, you know there is something going on there, right? And you can kill it. So yes, if you use PV calls, basically you use it for, I recommend to use it for monitoring more than anything else, right? Yeah, that's a basic overview of the architecture. A few POSIX calls are sent to the DOM0 over a ring. So as I said, because these networking calls are forwarded to DOM0 and executed in DOM0, actually the side effect is that all the ports are opened on DOM0 network interfaces, exactly like in Rocket host mode. So it's a great implementation of that networking mode for Rocket. It also works very well with VPN and wireless, any complex networking configuration in DOM 0, because the network access actually just happens in DOM 0, as if you were running your app in DOM 0. Interestingly, for security and as well for applying different network policies, something that I've not upstream yet, not even in the design document, is very, very easy to bind all the networking PV calls of one VM to one network namespace in DOM 0. This way, each VM can be bound to a different network namespace. And you can easily, this way, configure one VM, for example, NGNX, to be able only to open port 80 and 880 and forbid it from opening any other ports on your host. Right, so wrapping up, what is stage 1 Xen? Is stage 1 for Rocket. It works seamlessly, but it gives you a much more secure execution environment which supports multi-tenancy. Rocket works exactly the same, so your users will not be disappointed because there is no change from their point of view. It runs on bare metal and on the cloud, thanks to Xen PVGuest and PVH guest. It supports multiple networking models, so depending on your networking configuration, your settings, you can use bridging, net front, net back, you can use VFNAT, you can use PV calls, the ones that fit best your use case. And particularly PV calls today performs very well in comparison. Right, so the GitHub page is over there. It just started a month ago, so at the moment I am the only one contributing to it, but please join the effort. I'm using, I will reuse Xen devel mailing list for that. There are also, because the Rocket people are all very much excited about using the GitHub process for this stuff. I'm going to also take pull request, GitHub style. Yeah, I know. Life sucks sometimes. But okay, what can you do? Right, demo time.
Questions?
So what is the boot time and memory overhead of each of your containers? And are you recommending use of something like Intel Clear containers for faster and boot and low memory overhead?
So the overhead in terms of booting is about a second, one second time. The overhead in memory is about 2 megabytes, 4 megabytes, something like that. Now, I have done no work whatsoever to improve these two numbers. There is a lot of things that can be done. Yeah. And Clear Container certainly did some of this work, a lot of this work, and can be reused, I think, especially in the guest configuration. However, the problem with Clear Container is that it defaults to KVM, which again, it doesn't work on the cloud, and for us it's a showstopper, because by far most of the users use containers, cloud native apps in cloud environments. So we can't really support them with Clear Containers. The other problem with Clear Containers is it doesn't use the default KVM setup. It uses KVM tools or other tools, right, which are not supported from the security point of view. There is no CVEs, nothing, as far as I know. So it's really not, I think, viable for our use case at least.
Okay. Another question. So
yeah.
I didn't fully understand when you said you can run Xen Stage 1 on top of, let's say, Google Cloud Engine.
I'm going to show it right now.
Okay, but are you saying you're using nested virtualization there, or?
I'm using nested virtualization, meaning is yes, I'm running Xen inside a Google Cloud Engine VM. Okay. I'm not using nested VMX, meaning that in the Google Cloud Engine VM, there is no VMX. It's like pre-99, pre-2007 hardware.
Okay, thanks.
Yeah. All right. So this, in fact, is my Google Cloud Engine Aporeto page. I'm using Google Cloud Engine because Google Cloud actually gives free access to startups. So these VMs are free for me to run. I'm just gonna take one of the two. I'll start from this one. Right, okay. So there is an exited Nginx instance there. I'm gonna fetch. So you look at the command line is rocket fetch Docker because you're fetching it from the Docker registry. Nginx insecure option equal image because Rocket by default does security checks and the Docker registry does not support them. So obviously from this you understand the CoreOS people are really keen on their signature verifications and they force you to write down no signature verification so that you remember when you interface with the Docker registry that the Docker registry actually kind of sucks. So that's running the image. That's it. That's the overhead in startup time. Running the image, and if you saw, I specified stage 1 Xen as in the command line. I'm going to go up a bit. So I run the image I just downloaded from the Docker registry, interactive, to see something on the screen. Stage 1 Xen passed, I specified the stage 1 Xen I want to use. Insecure option equal image because, again, they want you to remind you that the Docker registry is bad. Now, the container starts, and you get, the classic Linux boot up, and then Nginx is started according to the command line option specified in the container manifest file. Now, SSHing into the box. And as you can see, there is a VM running. With the ID is the same ID of the container. If I do rocket list, it also comes up. You see the running instance there? So rocket list, I think the Docker works the same. As you can see, it also lists the containers that were previously run and then they quit. So you can see the running one and the exited one. And now, if I wget, now, and that's the Nginx intro page. What's interesting about this is I did it from localhost. Why? Because I'm using PV calls. So Nginx actually opens the port on the host. So now, outside the VM, I can wget from localhost, and I get the Nginx intro page. How am I doing on time? How much time do I have? Am I out of time?
Yeah, out of time, but what we'll do is we'll give you 5 more minutes for questions and stuff. I just checked with, we're all in the same room. We have a break coming up after the next set of sessions. It'll be fine.
So I'm going to show you very quickly another thing. That is, I'm SSHing into another host. And what I'm going to do is I'm going to show you one of the other networking modes. So this is the default in Rocket is a VIF-NAT script using net front, net back. I run a busybox container. So you can see here it has an IP address. If I did that with PV calls, you will see no interfaces. And I just got the Google intro page from there. The network was set up just using net front, net back as usual. And that's the Google stuff. Anyway, all right, that's the end.
So I'm kind of interested in this PV calls you keep mentioning. Is that a general purpose plumbing layer for system calls, or what is it?
Yes, it's a general purpose plumbing layer for system calls that at the moment implements the forwarding of only the networking related syscalls, which are accept, receive, message and message connect, socket, bind, those ones.
Right, so you have like some explicit little bit of code to format for each system call what the arguments are.
Right. But
so you're not doing, because one of the things that's scary about the sockets interface is it can get quite hairy if you forward too much of that. So you're not like implementing the craziness of set-sock-opt and things like that.
So at the moment, in fact, one of the ones that I'm missing is set-sock-opt. So basically, on one end, I have an incentive of not forwarding calls, because the fewer I forward, more security is. The fewer I forward, less work is for me, right? But on the other end, if application needs to some of these calls, they require them to run, I might have to add some. But I expect them to be still in the range of from 8 to 12 number of syscalls to forward, no more, right?
Right. So no like crazy raw sockets and weird ioctals and things. Great.
I'm just a bit curious, what about calls like send file? How does that work?
Send file?
Send file, yes.
Ah, right. So send file basically wouldn't work at the moment. It will, I think the implementation will fall back to the one based on send message and receive message.
Okay.
I just wanted to double check. So basically this is independent of PV or HVM, is it?
It's
because we have the
right.
overload of PV there for PV calls.
Absolutely. It's completely independent. As a matter of fact, I run this on ARM64. I consider bringing one of my other small ARM64 boards to run it there. But I thought that showing it on Google Cloud was, better. Yes, it defaults to PV if you don't have any VMX, because of course it's the only guest you can run there. But otherwise, if PVH is available, obviously we will use PVH.
Any more questions?
So you are using PV calls for example of network interaction. What about security? So if you expose some vulnerabilities in PV calls, it's possible to expose other virtual machines running on Rocket, right?
Yes, it's all a matter of trade-offs, as usual, right? So with PV calls, you have your surface of attack increases by about 10 new calls. On the other end, you have no net front, net back. Also, if you use PV calls, you should actually monitor this call. Otherwise, you might as well use net front, net back, right? So if you use PV calls, you should really build up information and track which are the port open in your VM to see if there is something going wrong, right? PV calls is mostly for monitoring.
I see. Thank you.
Do we have someone else? Okay.
So feel free to get any stickers from Rocket and CoreOS.
Yeah, everyone who asks questions, just go grab your t-shirts. We didn't really manage this properly, so we trust you not to cheat. And thank you.